Doppler effect is a shift in frequency in a wave, and the source and the observer are moving relative to each other. So if I get in this car and honk the horn while I drive by the camera, you should hear a higher frequency when I'm coming and a lower frequency when I'm going. Let's try that. When the car wasn't moving, we measured the frequency to be 1250 Hz. When the car was approaching, it had a velocity of 13.4 meters per second, and the recorded frequency by our microphone was 1296 Hz. When the car was going away from the camera, the car had a velocity of negative 13.4 meters per second, and our microphone recorded 1206 Hz. To derive the Doppler effect, we have to first look at the two different situations that can occur, and then put them together. The first being a moving source, and the second being a moving observer. To start off, this is a diagram of a stationary speaker. Each line represents one wavelength, lambda, and the speed of the wave can be represented by V and the frequency by F naught. In this situation, the source of the sound is moving at a speed V sub s, which is positive when moving towards the observer and negative when moving away. The wavelength of the sound perceived by the observer is lambda prime, and the perceived frequency is F prime. The difference between the original and perceived wavelengths can be represented by delta lambda. Delta lambda is equal to the velocity of the source times the period, or divided by the frequency of the wave. This, in the equation for the original frequency, can be substituted in to solve for lambda prime. That can then be used to solve for F prime, which gives us our first equation. The second situation is when there is a moving observer, moving at a speed V naught, which is positive when moving towards the source and negative when moving away. There is still a perceived frequency, F prime, but instead of a different wavelength, the velocity of the wave is perceived differently, represented by V prime. In a similar way as before, we can solve for the perceived frequency. The perceived wave velocity is equal to the original plus the velocity of the observer. That can be used to substitute into the equation for frequency, as well as the equation for the original wavelength, to give us the following. Putting both situations together, when there is a moving source and or a moving observer, the two equations can be combined into one final one that can represent any situation. Now that we have an equation for the Doppler effect, we can use it to find the perceived frequency in our experiment and compare it to the measured ones from our microphone. All we have to do is say F prime, the perceived frequency, is equal to the speed of sound, 343 meters per second, plus the speed of the observer, which was 0 in this experiment, divided by the same 343 meters per second minus 13.4 meters per second times the original 1250 Hertz. Doing this math, we get a final perceived frequency of 1300 Hertz. We can compare this to our original value from the experiment, which was 1296 Hertz, and we get a percent difference of 0.31% for the car approaching the source. When the car is moving away, we do almost the exact same calculation, except this time we use a negative speed for the source, which is negative 13.4 meters per second. This time it will shift it down because the car is moving away, and we get a final perceived frequency of 1203 Hertz. We can compare this to our measured frequency from the experiment, which was 1206 Hertz, and we get a percent difference of only 0.25%.